In the previous lecture, we worked out the direction of the magnetic field in a toroidal coil. Um, so just to remind you what it is essentially this tube which has now been bent in the shape of a donut, and you now wrap a wire around it. So you make this wire coil, and the current then that flows through it will create a magnetic field. And the way that the magnetic field will then add up from each coil, each loop of wire will add up. And what we found is that the magnetic field will basically loop around. The magnetic fields line will create loops inside the tube in the phi direction. So if I was to now draw my coordinate system and label this x, y, and z, and then what you essentially find is that that the field just wraps around in phi. So this angle phi right here. Okay. So now what we do is we have to work out what the functional form is so we can actually calculate the magnitude and go along with the direction. And so that magnitude we can use as Ampere's law. And Ampere's law says that the magnetic field dotted into the path is equal to mu0, the permeability of free space, times the current enclosed. Okay, so what kind of a Ampere loop should we choose? So if I look down in the z-axis down into the torus, then what I should see is my toroidal shape. There's some coils of wire, and the Ampere path I'm going to choose is this one right here, where I'm now basically cutting a plane through the cross section of the torus. Okay, so in that way, we are now going to have these. Basically, what we're going to have is our Ampere path, and then there are going to be current that is going to be, let's say, if the current is flowing in, it would flowing, say, let's say it flows into the surface here and out of the surface over here. So we're basically enclosing the current. The current is now going through, is going in through the top and then coming out through the bottom. And so this is the current that we're now encapsulating in our Ampere path. Okay, so now if we apply that, then basically the distance from the origin to the path, the magnetic field is going to be the same on every single point along this path because it's the same distance away from it. And so if I take my integral, then I can take the b out, it's constant, and also the b is in the same direction of the length L. So my length L would be, let's say, integrating in a counterclockwise direction. So the magnetic field would be going, and so the current would be going in. Actually, I want to switch that around and make my integration be in the clockwise direction, right there. Anyway, so the magnetic field's constant. Magnetic field is in the same direction. It's tangential to this loop, just like dl. So what I'm left with is now just the path. Whoops, not that. Just dl. So I'm integrating over dl. And this path here is a circle. So that length will be the circumference of the circle, where s is the radius. So this is my distance, this radius here from the center. Okay, and that's going to be equal to the amount of current enclosed. So the amount of current enclosed is the number of loops times the current in a single loop. And then I multiply that by mu 0. And so the magnetic field that I have now is mu 0, number of loops, times the current, divided by 2 pi s in the phi direction. Okay. So that gives me our result of how to calculate the magnetic field of a toroidal coil. It's a pretty simple result. And I should mention that this is now just for inside. On the outside, the field is 0. And so what we have is these two regions where you have the inside, and that's where we could use this equation. And on this region here, the magnetic field is 0. This region here, the magnetic field is 0. Only inside, basically, the torus shape do we get this equation of mu 0 n I over 2 pi the radius in the phi direction. Right. So that's our result. The next thing which I want to talk about is to kind of sum up what we've done so far with fields. And so in electrostatics, what we saw is that we could use Gauss's law. So the divergence of the electric field is the charge density divided by epsilon naught. So that's Gauss. So we also found that the curl of the electric field is 0 because, oh, not because of, but because of this result, we were able to write down that the curl of the gradient of a scalar is 0, and so the electric field we can write as minus the gradient of this scalar. Okay, so that was electric field. For magnetostatics, we have an equivalent statement for Gauss's law. Divergence of the magnetic field is 0. So I'm going to call it Gauss's law. But what it tells us is that the magnetic field lines have to form closed loops. And so there has to be, for a permanent magnet, let's say, both a north and a south pole, because basically any closed surface that we try to encapsulate around the source of magnetic fields is going to have magnetic fields that are going to be exiting. So if this is my Gaussian surface, I'm going to have magnetic fields exiting, but these magnetic fields are going to loop back and also going to be entering. And so we have these dipole fields that are going to give us a total flux of 0. Right. Lastly, we came up with Ampere's law, which said that the curl of the magnetic field is equal to mu 0 times the source, basically this current density, and for the most part, these are Maxwell's equations. These are the 4 Maxwell equations. They're not in the form that we're eventually going to use when we start talking about electrodynamics, But these are Maxwell's equations for statics, is when we have stationary charge creating electric fields or steady state currents creating magnetic fields. So just a few statements about that. We could add to our 4 equations now. So if I summarize our 4 equations, we have this. Okay, so like I said, these are all for static situations. And the last thing you might want to add to that is if we want to start talking about forces and calculating work, then the Lorentz force is the charge times the electric field plus the charge's velocity crossed into the magnetic field. Okay, and so some comments about those. So the first is that electric fields, so they diverge from positive charge and converge on a negative charge. So I have some positive, I have a negative. The electric field now is going to be going from positive to negative. Magnetic fields, they curl around currents. So if I have a current, I now have, moving in this direction, I now have a magnetic field which loops around the current like so. I've already mentioned that divergence of the magnetic field equal to 0 basically implies that the field lines have to converge back. So another way of saying that is there is no such thing, there are no magnetic monopoles. I can't just have a north pole magnet where I have the magnetic field diverging away from it. Every object that creates a magnetic field essentially has a north and a south pole to it. So there is no, so we can't separate them like we can electric charge. Electric charges, we still get the dipole action where electric field leaves a positive charge and heads toward a negative charge. But I could break that entity and move the negative on one side and the positive on the other side, and then just study, say, the positive charge. So the fourth comment is that the strength of these fields, for the electric field, the strength comes from the size of the permeativity. For the magnetic field, the strength comes from the size of the permeability. And these are just constants which nature has given us as to what their number should be. And last but not least, that B fields are created by currents or moving electric charge. Okay. So we're getting pretty close to the end of the semester, and so what we're doing now is, is basically summarizing all that we've kind of learned, and from there, everything has been applications. Applying Gauss's law to find electric fields, using the curl of the electric field to say something about this electric potential, using Biot-Savart law, but also Ampere's law to come up with magnetic fields. So the next step to kind of fill in this picture is to come up with an equivalent kind of potential for the magnetic interaction.